All right, so this is going to be a video all about Unit 5, the last unit of this course, which is all about applications of integration. Basically, this is going to be the entire unit in a nutshell right here in this picture right here. We're going to be going over stuff like area between graphs of functions, average value of a function, slope fields, modeling, volume, etc. So eventually you should be able to explain everything that's on this page. Now, this whole unit is based on the applications of integration. Integration, if you remember from the last unit, helps us solve one of the major problems of calculus, which is finding the area of any plane. So you say you have this non-basic shape right here, non-basic shape A. How do you figure out the area of this? Okay, with geometry, every shape that we dealt with pretty much had a very simplistic way of figuring out the area. But what if it's some curve f of x right here, and we're trying to figure out the area of this? This was all covered in Unit 4 using definite integral. So if you forgot anything from Unit 4, you're going to want to go back and review that on how to find areas such as this. All right, the first section of the unit is 5a, area between graphs. And basically, if you think back to the last unit, it's finding the area from the graph of f of x to the x-axis, like whatever the area is in between. The area between graphs is basically just as it sounds. It's the area between, say we have this function f of x and this function g of x. We're trying to find the area in between. And basically what you're doing when you're solving this is you're figuring out the area underneath f. So imagine the area underneath f to the x-axis right here. So it's kind of that weird shape there. And then you're subtracting off the area of g of x, the function of g of x to the x-axis, and it only figures out this area if you subtract that off. So the formula that you're going to use to figure out the area between graphs is going to be this formula right up here. A equals the integral from a to b of f of x minus g of x, all with respect to x. So that's basically all of 5a, using that formula and trying to figure out the area between graphs. Now make sure you understand this equation forwards and backwards, because a lot of times the problems are very procedural, but other times you have to kind of work backwards or use your understanding of this equation to solve a problem. So don't just kind of write this one off as easy. It is kind of complicated with certain problems. 5b is all about the average value of a function. So say we had a function f of x, like just look at this purple graph right here. If you can imagine, there's values of the f value, the y value of every single one of these. Imagine if you added all these values up right here in this purple and then averaged them out. Basically, it would come out to some constant. For example, this orange right here represents the average value of f. F is this purple function right here. And the way to figure this out is to use this formula right up here. Basically, what you're doing is figuring out the area underneath this purple graph. So if you can imagine the area underneath this purple graph right here, you are taking that area and then dividing it up by the b minus a. So it's like it's almost, the way I like to think of it is if you have infinitely many people and you line them up by their heights. So you just have a lineup, and their height is based on this purple right here. So if you can imagine infinitely many people lined up right here, if you took all of those people's heights and then divided by how many people there are, that figures out the average height of all those people, which is what you're finding right here, the average f value, which is the y. So it is kind of basically the height. Another thing you should notice when you find out that average value, to say it's this orange right here, you should notice the area above the orange. So if you can imagine this area right here and the area below the orange line right here, they should be about the same. Now this might not be the same because this is just for illustrative purposes, but they should be equal if you figured out the right average value. And the formula again is you just do the integral from a to b of that function. So you're finding the area underneath that purple, and then you're dividing it by the interval that you're using, this b minus a. Now again, these are all going to be filled with numbers. I'm just giving you the formula because this is just an overview video of the unit. The next section is probably the hardest section of the entire unit, 5c, volumes. Okay, with volumes, but what we're going to be doing is working with 3 dimensions. If you go back to what we started with, the area of any plane, so you're figuring out the area of some weird shape. Well, that means we should hypothetically be able to use this understanding, this weird shaped area, to figure out weird shapes of volume. So that's basically what 5c is all about. So if you have this function right here in the red, and say I revolved this function around the x-axis, this is called a solid of revolution. It forms a solid that looks like this. It looks like some kind of weird cone shape. Now you don't have to just revolve around the x-axis. You could also revolve around the y-axis. In fact, you could revolve around any axis you want, and you get similar shape right here than you do when you go around the x-axis for these. The formula for these is you have to integrate from a to b the area with respect to x or with respect to y, depending on the axis that you're rotating around. Now you might be thinking, well, what area am I talking about? Well, if you actually break up, imagine this shape right here. It's basically, imagine it, you just sliced it. You made infinitely many slices here. It forms basically a circle. So the area is basically going to be a circle here, and the radius of the circle is based on how high the y goes. So in this case, the circle would be, the area equation would be pi r squared, and the r would represent our f of x function. Same thing here, our x function, or in this case it's with respect to y, so it's going to be in terms of x. The radius would be based on whatever the value of this x function is right here, and then you're doing pi r squared. We're going to go into this more detail, but again, this is just an intro video of what the unit's about. Now, besides solids of revolution, we also have things with cross sections when you have a certain base of a solid. So an example looks like this. Okay, so say you had some function where we have this red and this blue right here, and imagine this is the base of a solid that we're going to be creating. And what we're going to be creating with it is squares that are perpendicular to the x-axis. So if you notice right here, this line right here is perpendicular to the x-axis. Imagine this line right here, a square is coming out of that line, so it's pointed toward you. Now, it's really hard to kind of picture that, so what I did is I made a graph, a three-dimensional graph right here that basically shows that. So it's got a graph, so this graph has basically squares that are pointed out. Imagine these are pointed toward you from this graph right here. And it's still color coded. You can kind of see the red and the blue function right here. And there's squares that are coming out of it. Well, imagine we wanted to figure out, if we had infinitely many squares popping out of this, what is the volume of that shape? So what I did right here, this is just 4 squares coming off of this base of this solid. Well, underneath it, I have one where it's 8 squares. And as you can see, these squares, like the base is a square here, and then that basically dictates how high it goes, because the square has to be equal on all sides. And so as the red and the blue get further away, the square ends up getting bigger. As you can see, the square is bigger in the middle here because the distance between the red and the blue function here are further away. But long story short, imagine there's infinitely many squares here, and you're just basically adding up the area of all these squares. That's what this is showing right here. So the volume is equal to the integral from a to b. In this case, this is our A and this is our B. So our A is 0, and then the B is wherever it intersects. It looks like it's just 1, 1. But we're going from 0 to 1 in this case. And you're adding up, remember this means summa, you're adding up all the areas. The areas of all these squares should be easy to find because it's just whatever the base of it is squared, and then you're doing that with respect to x for this one. You can do these with respect to y as well. I just didn't include any in this this overview. Again, this is just an intro overview, so I'm not going to have every single possible example. This is with squares. I also made a graph where you can do one with equilateral triangles. If you notice, this one has a few equilateral triangles. The one on the bottom has much more. If you had infinitely many, if you added up the areas of all of these equilateral triangles, then you find that volume. And that's, again, what this formula is saying on the right here. And last but not least, we have semicircles. This one has 3 semicircles. The bottom has 16. So as you can see, there's tons and tons more semicircles. You can see that it's forming closer and closer to that exact area. In this case, it's a semicircle, so your area would just be pi r squared divided by 2. Now, it is important to note that I just show the square equilateral triangle in semicircles, but you could technically have rectangles, you can have isosceles triangles, there's tons of other shapes you can do, but just know that the shapes that you are going to be using for these cross sections are always going to be basic shapes. But the base of the solid, to find that volume, is not going to be a basic shape. As you can see right here, it looks like kind of this weird teardrop thing. So we're putting basic shapes, basically these slices right here are basic shapes on a non-basic shape, and figuring out the volume for it. I used to have students do this project where basically they could cut pieces of paper and line them up on the graph. So they're just all y equals x squared. And if you cut the pieces of paper, this one's squares, this one's a triangle, this one's the semicircle, and this one is a rectangle. I used to have students do that. It is a good project to do, but it does take up a lot of time, and students are like, okay, we get the idea. Why did you make us cut all these pieces of paper? But it is kind of still cool to show how it works. I always think of it like post-it notes almost, that, actually change in size rather than a post-it note being all the same size. Just a way of showing this. It is kind of hard to picture this, so you're going to want to practice this as much as you can to really make sure you understand it. All right, next section is all about slope fields. Now, slope fields basically are just showing local linearization of a differential equation. So let's just focus on this thing on the left right here. This is basically what represents a slope field. It shows like say you didn't actually want to solve a differential equation, you can just plot a bunch of points and find the slope at each of those points, and it kind of gives you an idea of what the actual function would look like if you did the antiderivative of that differential equation. If you recall, differential equations were covered in Unit 4. If you forgot what those were, you're going to want to review those. But as you can see right here, it could help you find a family of what the original function actually looks like. And that's what I did on the right here. So it's the same slope field, only I actually graphed out certain equations that work with each slope field. So if you notice right here, right, they're all 0. So if I actually graphed one at 0, it would just go straight through the line. This one, if you notice, it follows along with what the slope field does. Actually, all of the curves actually follow along with what the slope field. So a slope field is basically just designed to give you an idea of what the family of functions, the antiderivative, would look like. These tend to be easier problems, so this is probably the easiest section of the entire unit. So the last section for this unit and the whole class is all about modeling. So basically with unit 3, we did modeling for derivatives. This is just basically going backwards to go to, instead of going from rates, but going to actual amounts. So one of the concepts that we went over in unit 3 was the derivative has the units of whatever f is. So f prime has the units of whatever the units of f was divided by the units of x. So if we were going to solve for units of f, because it's the antiderivative of f prime, f of x has the units of f prime times the units of x. So whatever the units of f prime is, you have to multiply that by the units of x, and then you find the units of f of x. Also in this section is going to be physics, but again, it's just, instead of doing the derivative, we're working backwards. So you might be given something like the acceleration, and you have to find the velocity from that, or given the velocity and find the position, and so on. So it is really important to make sure you understand all of these concepts. It's the same thing that we did in unit 3, only backwards, because we're going to be doing antiderivatives with them. So that's basically the entire unit of unit 5, applications of integration. You should be able to explain every single thing in this breakdown, this picture right here, which is also linked on the website, by the end of the unit. If not, then you are a little bit behind, but you should be able to explain these just by using this as your visual aid to a person that maybe doesn't really understand calculus, or maybe that does, but you just want to basically test how well you're understanding. So that's basically an overview of unit 5. If you have any questions about anything in this video, let me know.